Hello everyone. So today we will look into the hydrides of group 15 elements. So the various hydrides that are formed by the group 15 elements, the very common one that is ammonia, that is NH3, and less common the PH3, which is called as phosphine. Then we have ASH3, which is called as arsen. Then we have antimony hydride formed and called as stibine. Then we have bismuth hydride called as bismuthine. So these are the various hydrides that are formed by the group 15 elements. A common thing that you will observe for all these hydrides is that they are volatile in nature and they are very poisonous and foul smelling gases. Okay, often when we do experiments in lab, you have to check for the zero group. In that, you will heat your salt with NaOH and you will check the formation of ammonia. Ammonia has a very pungent and a foul smelling smell. So please don't at that time directly inhale that ammonia gas because it's a very poisonous gas. Try to keep it away because even if it's coming out in a very faint smell, you can easily detect the presence of ammonia. You need not have to bring everything close to your nose to inhale. So we are studying in theory, and now you know that ammonia is also a very poisonous gas. So make sure when you do the experiments, you are pretty careful while you are handling these chemical reagents. Okay. So here they are volatile in nature, they are poisonous and have a very foul smell. Now talking about the various strengths and property as we move down the group, what you find is the stability of these hydrides reduces. They decrease. The symbol I've written down here, it's actually signifying the decrease in stability as you move down the group. So most stable hydride would be ammonia. That is why it is very commonly found. But as you come down, you have very less frequency of them being reported in various reactions. So that is why you don't have much knowledge about these hydrides because stability wise, when we discuss, they are all unstable as you move down the group. Now, because of their instability as you move down the group, what is important thing to note is that the reducing power increases because as these hydrides becomes less stable, they decompose easily, liberating hydrogens which are available for reduction. And that is why the reducing power increases as you move down the group. Okay. Now, talking about their donor ability, some of you know that nitrogen contains a lone pair of electrons over it. Okay, so they act as Lewis bases. Okay, now similarly, all these hydrides should have a lone pair of non-bonding electrons, which can participate as bases. But the donor ability, as I have written down, they decreases as you move down the group. So when you move down the group, the donor ability kind of decreases. Okay, this is a very important property that you should trend that you should keep in mind. We will be discussing about the reasons in the next session probably. Today we will be just introducing ourselves to the various trends that are observed. In the next class we will discuss the reason behind these trends. Okay. Now coming to the boiling point, if you look at the boiling point, as you move down the group, the boiling point is increasing. Okay, this is pretty understood, right? It's a negative value. So it is increasing as you move down the group. That is pretty understood that as the molecular weight increases, molecular weight, the boiling point also will increase on account of some kind of van der Waals interaction. But what an abnormal thing that you will observe here is that the boiling point of the ammonia is pretty high. It should be lesser than this phosphine, but it is very, very high compared to even higher than the stibine. Okay. Now, why that high melting point you observe in the case of ammonia is the question. So it is very simple to understand because many of you remember when you talked about ammonia, they have the intermolecular hydrogen bonding that is present between the ammonia molecules. Okay, so when you talk about the intermolecular hydrogen bonding, you have your NH being hydrogen bonded to another N molecule, and you have the, so it's not coming out well. So you have your NH being hydrogen bonded to another NH3. So it is an intermolecular hydrogen bonding. Okay. So that is why, because of the intermolecular hydrogen bonding that is possible in the case of ammonia, you observe a higher boiling point. You observe a higher boiling point. Now, you will ask now why that kind of hydrogen bonding is not possible in the rest of the hydrides. That is pretty easy to understand, because if we look at the electronegativity value in the Pauling scale, you will find that the electronegativity of the hydrogen, which is approximately 2.1, is pretty close to the electronegativity of the arsenic, the phosphorus, arsenic, as well as the antimony. They are pretty close to hydrogen. So there is no much electronegativity difference between hydrogen and these phosphorus, arsenic, and antimony. And that is why the possibility of hydrogen bonding is greatly reduced. However, if you compare the electronegativity of nitrogen versus hydrogen, they have a pretty larger difference, and that is why the possibility of hydrogen bonding, it occurs in the case of ammonia and not in the case of the rest of the elements. So the abnormally high boiling point that you observe in the case of ammonia is because of the intermolecular hydrogen bonding that is possible in the case of ammonia molecules. Okay, so that gives ammonia molecule a pretty high boiling point. Coming to the preparation that of these particular compounds, you will find that the hydrides can be prepared from the binary metal compounds like magnesium nitride. When they are hydrolyzed, they lead to the formation of ammonia, or magnesium nitride when treated with the acid, that is HCl, they lead to the formation of ammonia. Ammonia, as you all know, they can be commercially prepared by Haber-Bosch process. Okay, you will be learning about these Haber-Bosch process. You will be talking about the Le Chatelet's principle that is involved here in the process. Okay, so this is the way that you prepare ammonia. Similarly, phosphine and arsine can be prepared by the corresponding binary compounds. Binary compounds means, binary metal compounds means it contains metal and another compound. So it's a binary compound. Only two types of elements you find in this compound. That is why it's called as binary metal. Metal because you find one of the element is a metal. So binary metal compound. So when you treat calcium phosphide with, when you hydrolyze them, you lead to the formation of phosphine. In the same manner, zinc arsenide, when you treat with HCl, it leads to the formation of arsine. Okay, so this is a very common preparation using the binary metal compounds. You can prepare easily the corresponding hydrides. Now, coming to the another method is the trihalides. These elements also form trihalides. So these trihalides can be reduced to get the corresponding hydride. Okay, so here this particular method is used for nitrogen, phosphorus, arsenic, antimony. All their trihalides, when you reduce with lithium aluminum hydride, it leads to the formation of the corresponding hydride of that particular element. Talking about the bismuth hydride, they are highly unstable. This I just now discussed. As you move down the group, the stability of the hydride reduces, and bismuth is towards the bottom of this particular group. So that is why they are highly unstable, and that is one reason why it is very difficult to prepare them. Even if you prepare it, usually they are prepared, they are very unstable and they decompose very quickly into bismuth and hydrogen. So usually they are very short-lived. hydrides. So there are not much common preparation you will get for this bismuth hydride. Whatever preparation is very in situ kind of preparation you do for these hydrides. Okay. So these are the general preparation that you do for the various hydrides of the group 15 elements. Coming to the structure also, it is very simple. You all know about it. Talking in terms of only nitrogen, I'm taking it. A similar explanation works out for the rest of the element. So I have used here the VBT, that is the valence bond theory, in order to discuss the structure. So here, talking about the nitrogen in its ground state, I have used the valence electrons here. So you find this is the ground state electronic configuration. Now, NH3 formation require 3 unpaired electrons to be present on the nitrogen. So that 3 unpaired electrons are present in the ground state itself of the nitrogen. So it need not undergo any kind of excitation. Therefore, in the ground state itself, they combine with the hydrogen electron to form the NH3 molecule. And here the hybridization is sp3. When we draw the sp3 hybrid orbital here, you see that one of the sp3 hybrid orbital is occupied by the lone pair. So the ideal angle for a sp3 hybridization is 109.28 minutes. 109 degree, 0.5, 109.5 degree or 109 degree 28 minutes. So these are the ideal angle for a system, for a structure with a tetrahedral orientation. Now, what happens here is that the lone pair kind of repel these bond pairs. Okay, so the lone pair bond pair repulsions are pretty greater than the bond pair repulsion. So because of that, they are kind of pushed closer to each other. They are pushed closer to each other, and that's why the bond angle kind of reduces from the ideal 109 degree to a value of 107.48 minutes. Okay, so this is the basic structure. That so if you are asked what is the shape of the ammonia molecule, you will write the shape is pyramidal. The shape is pyramidal. Okay, shouldn't write it is tetrahedral. It's not tetrahedral, but it is pyramidal because it has only, you consider the shape with the bond pairs. Okay, not take into consideration the lone pair while talking about the shape. So it will be called as a pyramidal molecule. Okay, so this would be the structure of the hydrides of this particular group 15 elements. So in the next class, I'll be talking in more detail about the bond angle that is formed by the rest of the hydrides. So what I would like you to do before I post the next video is that go and check for the bond angle. Here, ammonia, the bond angle is 107 degree. But for the other elements, you will find a greater reduction in the bond angle. So just go and see for the bond angles and try to write them down in the notebook. In the next class, we will discuss why there is a greater contraction in the bond angle in the rest of the elements. So thank you very much for your attention. Let's meet for the next